What can you do with a transistor? Well, let's take an example. You remember turning on an LED. We often used a 1,000 ohm resistor. If you've ever measured it, you probably found out that the current going through this circuit was something on the order of 3 milliamps, and that made the LED reasonably bright. Suppose you wanted to turn on an LED by pinching something with your fingers, because your fingers will conduct electricity a little bit, but not very much. The resistance of your fingers may be about 1,000,000 ohms. Well, you could say, I'll set something up like this. Here are some places I can pinch with my fingers, which are equivalent to maybe 1,000,000 ohms. And I'd like that current, if it happens, to go through an LED and light it up. That won't work very well because the current going through here is only on the order of a few microamps, unless you get your fingers wet and squeeze real hard. Maybe that would help. But anyway, it's hard to get this to work well. Let's use our current amplifier, the transistor, to make this work a whole lot better. So now I'll have my +5 rail. Here's the places I squeeze with my fingers to say that I want this LED to go on. And I'm going to run that current now through the base to emitter junction of a transistor to ground. So this is the base, this is the emitter. This current, a few microamps, is going to be flowing this way, and it's going to allow a much larger current to flow from the collector to the emitter. And that's where I'm going to put my LED. So here's a light emitting diode. Now, if a few microamps rather flows this way, that gets multiplied by the current gain of the transistor, something like 100, and the current that's going through the LED is going to be several times that. Instead of a few microamps, it's going to be several hundred microamps. And that'll make the LED glow nice and bright. That's something you can actually build. It'll work for you right away. Now, let's see what happens when we do this in a more controlled situation. What happens as we continue to increase the base current? Can the collector current increase indefinitely? Well, it can for a while. And in fact, in this case, eventually that collector current will be so great that you'll probably burn out the LED. So let's do this with the resistor instead and take a closer look at the voltages and so on that develop. I'm going to put a fixed 1,000,000 ohm resistor here for now. Here's a transistor with the emitter connected to ground. And now I'm going to put a resistor in the role that LED had over there. Let's make it a 1,000 ohm resistor. Now initially, if we open this circuit here, no base current flows, and therefore no collector current flows. And so if we evaluate the voltage that's across that 1,000 ohm resistor with no current flowing through it, the voltage across it will be 0. And of course, therefore, the voltage from the collector to the emitter of that transistor will be the full 5 volts. Now let's carefully increase the base current and see what happens to the collector current and so on. So I'm going to reconnect this 1,000,000 ohm resistor. Now we know that about 4 microamps is flowing this way, and the 4 microamps of base to emitter current gets multiplied by the gain of the transistor of about 100, so we expect that there should be about 400 microamps flowing here. Let's think now. 400 microamps through a 1,000 ohm resistor is about 0.4 volts. So this measurement is now 0.4 volts. Having deduced that, the rest of the voltage, the rest of the 5 volts, if 0.4 is here, this voltage here must be less, must be 4.6 volts. Okay, so the collector to emitter voltage of the transistor has reduced from 5 volts when it was off to only 4.6 when it's a little bit on. Let's continue the process. Suppose I make this not 1,000,000 ohms, but 100,000 ohms. Now we've got not 4 microamps, but 40 microamps of base current. We've got not 400 microamps of collector current, but 4,000 microamps, 4 milliamps. And the voltage across this 1,000 ohm resistor is not 0.4 volts, but rather 4 volts. And that leaves only 1 volt from the collector to the emitter of the transistor. you can see where this is going. What happens if I increase this base current still further? Soon, if I reduce this to 10,000 ohms, this will be 400 microamps. Your calculation would say this is 40 milliamps, the voltage across this resistor with 40 milliamps through it is 40 volts. Whoops, how can that be? It can't possibly be that there'd be 40 volts here, and therefore we'd have to say negative 35 volts across the transistor. Something has gone wrong, and that something is this transistor can never reduce its collector-emitter voltage below 0. The best you can do here is put enough current from base to emitter so that the collector to emitter voltage goes down to 0. That condition is called saturation. That happens when the voltage from the collector to the emitter of the transistor is 0. In fact, not even quite 0. There's a statistic, a specification for each transistor that tells what is the voltage from the collector to the emitter in the case of saturation. And it's usually less than 1/10 of a volt or thereabouts, maybe 0.06 volts for the transistor that you're using, close to 0. But you can never get that voltage to go below 0, and no matter how much base current you put in, and essentially it's wasted beyond the point where you reduce the collector emitter voltage to its minimum value.